Earlier we started to describe a systematic way to think about velocity changes, or equivalently, momentum changes of an object whose translational motion we're observing. We want to develop methods that apply generally to a wide variety of different cases. So, as one example, imagine what we're showing here is the path in space that an object traces out as we watch it move, in some general way, over some extended period of time. We sometimes call this path the trajectory. What we want to do here is to consider the object at some point on its path and systematically describe how the motion is changing at the corresponding moment in time. As we discussed earlier, at any point on the object's trajectory, there's a natural way to choose a coordinate axis parallel to the direction the object is moving, and that changes to the velocity and momentum along this direction are related to the speeding up or slowing down of the object. We also mentioned that changes to the velocity and momentum that are perpendicular to this direction are related to the curving of the object's trajectory. To characterize this more formally, we're going to look closely at a physical quantity related to both delta P and delta V, that is, the ratio delta P over delta T. Now, since we typically look at motion as time advances, so that Tf is later than Ti, delta t is typically positive. In this case, the vector delta p over delta t is just delta p divided by a positive scalar. So, delta p over delta t points in the same direction as delta p. And for that matter, it points in the same direction as delta v. We can decompose delta p over delta t into parallel and perpendicular parts, just like we did for delta p and delta v. The parallel and perpendicular components of delta p over delta t have the same sort of meaning as those of delta p. Namely, the parallel part of delta p over delta t is associated with the object speeding up or slowing down, while the perpendicular part is associated with the object changing direction. We'll now show in a moment how this decomposition can be derived for delta p over delta t. This will be very useful when we link these motion changes to the net force because delta P over delta T is directly related to F net. However, we want to emphasize that today we're focusing only on quantities we can learn from direct observation of the motion, plus knowledge of the system's mass. We'll discuss in later lectures how to relate these observations to F net itself and to the specific interactions that contribute, that add up to give us the net force. Now, to decompose delta P over delta T into parallel and perpendicular parts, let's start with the idea that when delta T is sufficiently small, the ratio delta P over delta T is a good approximation to the derivative dP dt. Also, as we know, we can write the vector P as the product of its magnitude and its direction, expressed as the unit vector p hat. This means we can write the derivative dP dt as the derivative of the product of the magnitude of p times p hat with respect to time. Now, since the magnitude and the direction of the momentum can each change with time, we must differentiate this product using the standard product rule for derivatives, and we end up with two separate terms. We examine each of these terms separately to understand what each means physically. Looking at the first term, we notice that this vector points along p hat, which means this vector is parallel to the direction that the object is moving. In other words, p hat, and for that matter, the velocity unit vector v hat point along the parallel axis we discussed earlier. For this reason, we sometimes refer to this vector as dP dt parallel, the parallel part of the full derivative dP dt. Now, we discussed earlier that motion changes along this parallel direction are associated with speeding up and slowing down. To see how that shows up here, we will need to calculate the derivative of the magnitude of the momentum with respect to time. We have to be careful with our language here. The derivative of the magnitude of the momentum is not the same as the magnitude of the derivative of the momentum. The former is only related to how quickly the magnitude of the momentum is changing, while the latter is related to how quickly the momentum is changing, including any change in direction. To get some idea what the derivative of the magnitude of the momentum means, let's consider this specific case. If the time delta t is small between the initial and final momenta shown, then we can obtain a good approximation to the derivative d magnitude of p dt using delta magnitude of p over delta t. Notice that the numerator here, the magnitude of p final minus the magnitude of p initial, is a scalar, and it simply means subtract the magnitude of the initial momentum vector from the magnitude of the final momentum vector. In this case, this scalar subtraction just gives us a positive number because the magnitude of p final is larger than the magnitude of p initial. But this just means the object is speeding up. Dividing all this by delta t still gives us a positive scalar, so that when we multiply all this by p hat, we end up with a vector that points in the direction of p hat like this. Let's be careful to notice that delta magnitude of p over delta t is the scalar change in the momentum vector's magnitude, and so is not the same as the vector delta p over delta t. Let's consider another example here, where once again delta t is small between p final and p initial. However, we see here that p final has a smaller magnitude than p initial. What would be the direction of dp dt parallel? In this case, when we subtract the magnitude of p initial from the magnitude of p final, we get a negative number, even though both the magnitude of p final and p initial are positive. It's negative because the magnitude of p final is smaller than the magnitude of p initial, so the subtraction gives us something that's negative. Also, we know that p final having a smaller magnitude than p initial means the object is slowing down. Dividing all this by delta t still gives us a negative scalar, so that when we multiply this by p hat, we end up with a vector that points in the direction opposite to p hat like this. Now let's look at the second term from our vector derivative of dp dt. You might guess from our previous discussion that this second vector term might be associated with the curviness of the object's path, and moreover, that this term points in a direction perpendicular to the direction of motion of the object at the moment we're looking at the object. That would be a good guess because it's correct. We can symbolize this perpendicular part as dp dt perpendicular using the perpendicular symbol. We're now going to give a geometric description of what this term means. First, let's recognize that at the instant we look at the object moving on a trajectory, there is, in general, a unique circle that smoothly fits the trajectory at the location where the particle is located. By smoothly fits, we mean here the circle is tangent to the path at the location, and the circle has the same radius of curvature as the trajectory at the object's location. This circle is scarily known as the osculatory circle, or as the textbook calls it in more familiar English, the kissing circle, because the circle smoothly kisses the trajectory. With this circle in mind, we can discuss more concretely the meaning of dp dt perpendicular. The textbook uses the kissing circle to describe a geometric way to perform the derivative of dp hat dt, and we will quote the results here. The direction of the vector dp hat dt is the unique direction that is perpendicular to p hat and points from the object toward the center of the kissing circle. The magnitude of dp hat dt is equal to the magnitude of the velocity divided by the radius of the kissing circle. Let's now summarize all this. We use calculus to decompose the vector dp dt into two separate parts. One we call dp dt parallel, and one we call dp dt perpendicular. We discussed how the first part, dp dt parallel describes either speeding up or slowing down, depending on whether the scalar delta magnitude of p over delta t is positive or negative. In other words, whenever we observe the object to be speeding up or slowing down, then we expect this term to be non-zero. By contrast, when we see the trajectory of the object exhibiting curviness, then we expect the second part, dp dt perpendicular, to be non-zero. More specifically, the direction of this term toward the center of the kissing circle tells us something about the direction that the trajectory is curving, and the magnitude of this term, the magnitude of p times the magnitude of v divided by r, gives some indication of how sharply or how gently the trajectory is curving. For example, a small r corresponds to sharp curves, and a large r corresponds to gentle curves. Armed with these rather detailed descriptions of motion changes, we're now in a position to state how these changes are related to the total interactions, the net force. Because, as we said, dp dt is directly related to F net via Newton's second law, the decomposition of dp dt into parts will help us to describe a similar decomposition for F net. We'll discuss how that works in our next lecture.